First thing I want to do is to just start building our repertoire, our list of functions and series. And I'm going to keep this on a separate page. If you want, I would recommend, if you're taking notes, keeping this on a separate page as well, just because we're going to build a table. And then as we do some other work, we'll come back to this. So power series, Taylor series, and Maclaurin series. So right now, let's make our table, our function. So first function we started with was 1 over 1 minus x. And then we've got our series of just x to the n. And then the radius we should probably list as well. So absolute value of x less than 1. And then yesterday we worked out arctan. And our series for arctan we saw was an alternating series, 2n plus 1 of odd terms. We derived this from the geometric series. It's also going to have a radius of 1. And so our goal for today is to fill in the rest of this table. The other standard functions that we like to use are natural log of 1 plus x. This one's going to be fairly easy, so we're going to continue along our lines of what we were working with yesterday. We can derive this one from the geometric series. And then we want to get through our other standard functions that we like to use. So we're going to need an exponential, and we'll typically just start with e to the x. We've got, and then our sine and cosine are our other key building blocks. So of course, other exponential functions, we can actually just modify from e to the x, right? If we change the base, we can just write, e to the natural log of b times x to change the base. And then we could substitute that into the series to come up with a different geometric or a different exponential series. Sine and cosine are our building blocks for our trig functions. Sine and cosine, of course, when we divide them, we can get tangent, cotangent. The other arc trig functions like arc sine, arc cosine, those are a little tricky, especially with the square root. We'll see the technique of how to go about doing that. And then there are potentially other functions. There's hyperbolic functions, which show up in the book occasionally, though we haven't worked with hyperbolic sine or hyperbolic cosine. When you guys were in Calc 1, did you guys use hyperbolic sine, hyperbolic cosine?
Yeah, we did.
You did? Okay.
Yeah.
So we may want to add those to the list as well. Hyperbolic sine, hyperbolic cosine are actually pretty easy. They're the same as sine and cosine, except they're not the same. They behave very similarly in their cyclic nature. So looking through those might not be bad, just so we have a broad scale of all the types of functions that come up. We've got our logs, we've got our exponents, we've got trig, hyperbolic trig, and then at least some of the inverse trig. We won't be able to come up with all of them on our own, at least during lecture. We're not going to have time to go through them all. But as we will see with Taylor series, you should be able to understand the process of going about finding these. So right now, our only process is modifying the geometric series. So let's go ahead and do another one of those since we can do natural log that way. And so let's warm up with that. And then real quick, we're going to talk about evaluation of series and how we can evaluate series based off of known power series. And then we'll come back to this page and we'll fill it in as we develop these guys. Yeah, I'm looking in the book, like if you have on Taylor series, they put in hyperbolic sine and cosine in there. I know in the math department, we don't really teach those. They're not terribly difficult, especially if you know the exponential forms of those. Maybe we'll at least mention that. And then when we get in the Taylor series, we can see if they'll come up in examples. Okay, so let's do find a series. And our convergence radius for natural log of 1 plus x. So the thing we want to notice about natural logs is that when I take derivatives of natural logs, they turn into rational functions. And we know how to get Taylor series, how to get power series for rational functions. So this equation essentially says that if we integrate both sides, the natural log of 1 plus x should be the integral of 1 over 1 minus negative x dx. And so we can use our Taylor series or power series techniques. Sorry, I might say the different words. If I ever say Taylor series or power series or Maclaurin series, they're all essentially the same thing, as we'll see. The only difference, sometimes when we say Taylor series, we mean a finite sum of terms. But in general, if we're considering the full series and infinite sum, they're all essentially the same. So we need to integrate our geometric series. So we have minus x to the n. And so it's this step here that we want to require that absolute value of x should be absolute value of the argument. Absolute value of minus x is less than 1, which is, of course, the same as absolute value of x less than 1. So that'll give us our radius here dictated by our series. So we just need to integrate. I'm going to go ahead and write this as a sum. We can pull out the minus 1 to the n, and then it's just going to be an integral of x to the n dx. And that's an easy integral. And we just got to be careful of where our starting value is. So we start at n equals 0, and with integrals, we are potentially adding on a constant. So we notice that the starting value is n equals 0, but when I plug in n equals 0, it'll start with our linear term, x to the 1. So there could be some constant term added in there that we need to solve for. So to solve for it, we typically pull that constant outside of the sum. So c plus n equals 0 to infinity, minus 1 to the n, x to the n plus 1 over n plus 1. And then how do I solve for the constant? We plug in values. So easiest value is always natural, or is x equals 0. And then again, be careful when you're evaluating these, especially at 0. since the first term starts with our linear term, when I plug in 0, the entire series is going to vanish and only leave us with that constant term, which means our constant term is just 0. So we didn't need it. 0 constant term, which means we have a nice power series representation of natural log of 1 plus x. So as we derived it here, it's going to look like this. It's commonly written re-indexed starting at 1. So if we're starting at 1, well, the first term here, think when n equals 0, the first term we're going to see is x to the 1 over 1. So all we're really doing is just going to now have x to the n over n. When n starts at 1, we'll have x to the 1 over 1. When n equals 2, we'll have x to the 2 over 2. Likewise here, it's just going to be shifted a little differently, shifted off by 1 on the index. N equals 0 gives us that x to the 1 over 1. N equals 1 gives us x to the 2 over 2. And then so we just need to shift the index on the alternating part as well. So that is our natural log. Let's go ahead and fill that in on our table here.
Can you go back for just a second? Real quick?
Oh, sorry, sure.
Thank you.
So it's a pretty easy series. It's alternating. It's just x to the n, and then the sequence of coefficients is just 1 over n. And our radius for this guy was less than 1. So those are our 3 functions. These two, of course, we built from our 1 over 1 minus x, but it's nice because these 2 functions are pretty standard functions that we have seen a lot of throughout all of calculus. So having to rederive them if we're trying to work with series isn't necessarily good. So it's kind of good to have our basic standard repertoire of functions and then being able to pull up the series. Definitely recommend you guys memorizing this, or at least know how to quickly go through those steps and rederive the ones you're not sure of. So let's take a look at some examples of what we can do with power series. Let's say find the sum of the series. Or it might say determine whether the series converges or diverges. If it converges, find the sum. So our series is just going to be n equals 0 to infinity minus 1 to the n times 4 over 2n plus 1. So the first thing we would check, converge or diverge. Hopefully this one's fairly quick. Converge by the alternating series test. Hopefully it's pretty clear that without the alternating, our sequence of individual terms, something like 4 over 2 to the n, 2n plus 1, it's going to be decreasing monotonically. And then it's also going to, the terms are going to 0. So it passes the divergence test, decreasing. And then with the alternating part, it's going to converge. And so now our question is, how do we actually find the sum? We want to look for known power series that look similar. I.e., the coefficients in the power series look like our series. They're never going to be exactly the same. But what you want to look for, sorry, let me finish this sentence, look like the given series. What you want to look for are rates of growth and the types of functions that involve that our series behave like. So is the series behaving like 1 over n? Is it behaving like 1 over n squared? Is it behaving like 1 over n factorial, which we'll see? And then you want to match it with our table. So when we look at our table, right now we only have 3 functions. And we've seen a lot of examples that we should be good at recognizing geometric series now. If it were something like 4 to the n or 1/2 to the n, we would certainly have something like something raised to the n. We want to look to match the coefficients as well as any exponential part. So I guess we should mention that as well. And I'll put that in quotes. Right, the big basis of all of these power series and Taylor series is that a sequence of increasing powers of x, like a polynomial, is a geometric series. X to the n, x to the 1, x to the 2, x to the 3. And so if I plug in a number for x, it's going to look like a geometric series, an exponential series. However, as we've seen with arctan, is sometimes that exponential, it isn't just x to the 1, x to the 2, x to the 3. Sometimes, like in this case, we have x to the 1, x to the 3 is going to be the next term, x to the 5. So it's only going to have the odd powers in the exponent. And we'll see something similar once we get down to sine and cosine. So that's kind of why I put it in quotes. That's another way you can identify it is there any sort of exponential term here? And if it is, is the exponential all of the numbers? You know, was it 4 to the 1, 4 to the 2, 4 to the 3, or is it the odd exponents? So it's another thing to look for in order to match these. So hopefully it's kind of jumping out at you that we have this 2n plus 1 in the denominator. And right now, the only series we have with a 2n plus 1 in the denominator is our arctangent. So we want to try to phrase this series in terms of arctan. So since we have we want to look for arctan power series. Namely, if we start with our series, be careful with the way it's written. Notice that I don't have any sort of, sorry, that's a 2n. We don't have any n's touching this 4. It's just a constant. So we can actually pull that out. And so here's our series. And if we're comparing it with arctan, our power series for arctan, the only thing that's missing is what value do I need to stick in for x? So what value for x gives our series? And I guess if we wanted to be a little more clear to match them, I can always multiply on the outside of a series by 4, same as multiplying on the outside of the function by 4. So now we see how closely those match up. Now we just got to figure out what x value do I stick in here in order to get this exact series. Well, there is no term that says 2n plus 1 that's raised to the 2n plus 1 over here. So hopefully everyone can kind of see that we just got to stick in x equals 1. If x is always 1, 1 to whatever power is always going to be 1, and so this term is going to look like it just goes away when x is 1. And we are just left with our coefficients. Meaning that this series is just going to be 4 times arctangent of 1. And what's arctan of 1? Everyone knows and loves, and it knows how to evaluate our inverse trig functions. Arctan of 1 is pi over 4. So 4 times arctan of 1 just gives us pi. So this is a fairly big result in mathematics, especially in computations and computers. What is pi? We know that what pi is geometrically, and we've defined it as the ratio of the circumference to the diameter of a perfect circle. But how do you plug that into a computer that only understands ones and zeros and binary operations? With binary operations, we can plug in sum, addition, program multiplication. So how do we get pi? How do we program pi? And how do we program computers to compute pi? Any of those computers and those algorithms that you see pi computed to 1,000,000 decimal places or something, generally is going to use a series. What we actually have is a series of rational numbers. So this is just, so 4 over 1 minus 4 over 3 plus 4 over 5 minus 4 over 7. And it's going to keep going. Meaning I have a sequence of rational numbers that when I add and subtract and do this ad infinitum, it will ultimately compute the exact value of pi. So this is something that a computer can do. And if we wanted to compute pi now to a certain degree of accuracy, we could compute a certain number of terms to get a very accurate representation. Any questions on that?
So at the beginning, you proved it was convergent. Was that just so you could prove that there was a sum, or like there was a finite sum? Or
Yeah, exactly. I really put it just because sometimes that's what the problem statement says. We've seen that on some of the homeworks. I think actually on this current homework or the previous homework for sure. When we were working with geometric series, it said prove whether the series is convergent or divergent, and if it converges, find the sum. So sometimes we first have to prove whether it converges or diverges. I didn't write that in the problem statement, but always good to show or at least understand why it converges. Because, of course, you will have to do that on the midterm. There will be problems where you have to determine whether a series should converge or diverge. And then now you might potentially have to find the sum of a series. And now, instead of just using geometric series to find the sum of a geometric series, now we have a whole list of functions that we might have to evaluate based on recognizing power series. So maybe we'll do another one of these. The other good ones to recognize, of course, at the moment are going to be natural log. So if you're looking at a series, or if you're trying to evaluate a series and you only see the denominator as n, it's an alternating series with a denominator as n, and then you see some number that looks like a geometric series, you can evaluate that as well with a natural log. Maybe we'll see an example if we have time at the end. Let's go ahead and move on, and let's try to finish this table and fill in our base functions, our building block functions, e to the x, sine of x, and cosine x we want to determine. So we need new methods for that, because e to the x, sine of x, and cosine of x, all three are actually highly related to each other, but they're not related so much to our geometric series. So we need some general methods. So in general, our question is, how can we find a series for some function f of x? So another thing we can ask is, let's label that as question and another question. Given a function f of x, can we approximate the function at a point with a polynomial? As we just saw, polynomials are nice. We can even approximate a number like pi, which is not only irrational, it's a transcendental number. So if you guys have to take higher math, you'll learn what that is. It's in some sense, you can kind of think of it as just a more complicated number than even irrational numbers. We like rational numbers. It's just quotients, fractions. Those are pretty nice and easy to compute, easy for a calculator to compute. And then we have what are called algebraic numbers, which give us a set of irrational numbers, things like square root of 2, square root of 3. Those are both irrational. And those we can compute at least as zeros of polynomials. Pi, you can think of as even more complicated than that. Same thing with e. Very complicated numbers. And so if we wanted to approximate these types of numbers, it would be nice if we had some sort of rational series to be able to approximate them with using polynomials. We like polynomials because it's just, especially with rational coefficients, it's rational numbers. And then if we plug in rational values of x, we can compute things very easily. Another way we want to think about it is, suppose we have a function. So here's what we were doing in Calc 1. We have some function. And what we would do is, say we wanted to approximate the function at, say, x equals 1. So we find x equals 1, and maybe we can't compute that value, or let's do this. Approximate the function at x equals 1.1 by a tangent line at x equals 1. So hopefully you guys saw some of those. So what we would do is, at x equals 1, we would find the equation of the tangent line. And we notice that on really short distances, that tangent line is really close to the function. And so if we want to approximate 1.1, instead of actually computing e to the 1.1 or natural log of 1.1, we could compute the value of the function at a nearby number, that's easier to compute, and then just follow the tangent line. Actually compute the value of 1.1 on the tangent line. And it's not going to be precise. It's not going to give us the exact value of the function, but it'll be close, right? And so what we found was, I like to use L of x. So L of x is the tangent line. This formula should look fairly familiar. And let's say, so at x equals 1, we computed the value of the function at x equals 1, and then we added on some sort of dx, where our dx in this case is maybe 0.1. So we are deviating from the center of the line, or our basis point for the line, by 0.1. Oh no, sorry. I'm doing this wrong. This is our dx. F prime of x. F prime of 1. We want to create a vertical line. Let me rewrite this. Should have had this formula, where this we kind of consider as our delta x from our base point. So if our base point is 1 and we plug in 1.1 for x, that would give us our delta x, our change from that point, times our f prime of x gives us the slope, and then f of 1 gives us the starting point. And so the second question, what we could do is phrase as, can we become more accurate? We used a line, and as we know, the function isn't a line, so it's going to deviate away as we move further along the line. We're going to have a bigger amount of error. So can we make it more accurate? What if we want to include something like maybe a quadratic? In other words, what if we wanted to find an approximating parabola? So we have our function. Instead of having a tangent line at 1, which as we saw started to deviate fairly far away from our function, what if instead we kind of developed a method to find the closest approximating quadratic polynomial? So then we could match not only that point, it would have to match the slope at that point, but then the second derivative, the curvature that's defined at this point by the function, we would also be able to match with this parabola. So what would this look like? Let's call this t of x. It's going to be some polynomial, some quadratic. And actually, let's change this base point. Let's pick it an arbitrary base point where we are approximating and call it a. And we want this to be close to f of x, especially near values close to that base point, close to where we want to approximate it at. So what would this look like? Is there a way we can solve the best coefficients. All we've done so far is set up a generic degree 2 polynomial, specifically centered at x equals a. So we know at least now if I plug in a, we get a constant. So we want this polynomial at the point a. Well, at the point a, it should be equal to the value of the function. And what does that tell us? Well, t of a, as we just mentioned, when I plug in a in the x, we see the nice thing about writing a generic polynomial in such a way is that it is centered at a, meaning that all of the terms are going to vanish, and we are just left with that initial constant. And that initial constant has to be the value of the function at a. Okay, so our parabola matches the function. What else are we going to want at that parabola? Well, if we want it to be close to the function, we should match the first order derivatives, namely the tangent line at this point. A tangent line approximation should also be the same tangent line approximation to that parabola. They should have the same slope, the same rate of change. So we should have that t prime of a is also equal to f prime of a. So if the first derivatives are the same, what does that tell us? Well, t prime of a, that c0 is going to drop off, and we are just going to be left with c1 plus 2 times c2 times x minus a to the 1. And then when we evaluate it at x equals a, we simply get c1. And so the requirement that our first derivatives are equal tells us that this first coefficient, or c1, has to be equal to the derivative of f at a. And so this is what we're going to see. When we have polynomials and when we have series that are centered at a given value, the coefficients are going to correspond and be directly related to the derivatives of the function. So if we were to keep going, well, we have a parabola. We've matched the point. We've matched the first derivative. If we want the second derivatives to match, which would give us the same concavity at this point, so having the same rate of change and having the same concavity, starting from that same point, is going to give us a very accurate representation and a very accurate way of approximating the function within perhaps a bigger range than we would with just the tangent line. So our second derivative if we need those to match, is going to give us the equation, well, t double prime of a, we're going to take one more derivative from the first. That's going to kill the c1 constant, and we will have 2c2 times, that x minus a will then be to the 0. So it'll just be 2c2. And then even evaluated at a, we're still going to get 2c2. And we need that to be equal to our second derivative. In other words, our c2 is going to be f prime double prime of a over 2. Everyone with me? So, to summarize, given f of x at a, let's say at x equals a, we know that f of x can be approximated by a polynomial that looks like this. This first part I'm writing should look very familiar. This is just the linear approximation. That's our tangent line. And then if we need to include the next term and want to include an approximating parabola, we found that the coefficient, our second coefficient of this parabola, is going to be related to the second derivative. So this is what we would call a second order approximation. Our value at the point is the 0th order. First order approximation is our linear approximation. Second order approximation gives us a quadratic approximation of the function centered at x equals a. And so, of course, the natural question to build from here is, well, what if we want to get even more accurate? What if we wanted to get infinitely accurate? What if I wanted an infinite polynomial, in other words, a series, to represent our function? So we want something like f of x to be represented by some sort of series up to an nth degree and potentially beyond if we want to take infinitely many terms. How would that look? And can we find the best coefficients? Well, I have this approximate sign equal there. At the point A, we could declare absolute equality. And if we knew something about the radius of convergence of the series we're trying to define, we can actually prove that those two things are exactly equal. So assuming we're in a nice enough radius of convergence and that we do want equality, we can essentially find a formula for these coefficients. Namely, what did we find? We find that C0 is going to be the value of the function at A. C1 is going to be the derivative, first derivative evaluated at our base point. C2 we found was related to the second derivative. Let's do one more, maybe two, to try to see what's going to happen. So if we, let's call this big series. Let's call this T of x again. If we were to go one more time and dictate that we want the third derivatives to match, what is that going to say? Well, now we're taking three derivatives of our Taylor polynomial. The first derivative is going to kill that term. This term will go down to x to the 0. Second derivative we saw kills the linear term. Our third derivative what's going to happen? So we're going to have d dx of the second derivative. So the second derivative was 2c2 plus 3 times 2 times x minus 1a to the 1 plus 4 times 3 x minus a to the 2. And if we compute one more derivative beyond that, the quadratic, term, our quadratic coefficient, is going to vanish. And then we're going to be left with 3 times 2. And I forgot my C3 here and a C4 here. 3 times 2 times C3 plus 4 times 3 times 2, C4, x minus a. And then, of course, evaluating at x equals a, we're only going to get that constant term. In other words, our C3 is related to the third derivative of the function divided by 3 times 2. So does everyone see that? If you didn't follow, write that out, right? We have this formula for t of x. Take one derivative, see what you get. Take another derivative to see what you get. We are essentially expanding upon this process we did in the previous example, except you can now imagine that if I have a plus c3 times x minus a cubed, we now have to work with this term as we take 1, 2, and then 3 derivatives to see what's happening with these coefficients. So of course the coefficients are gonna stay there every time we take derivatives, except for when they are the constant term. And then whatever degree they are associated with, so our C3 was associated with our degree 3 term. Every time I take derivatives, by the power rule, we're going to be pulling down that coefficient. So after one derivative, we had that 3, 2 derivatives, we had the 2. And then when we take another derivative, we are essentially pulling down the 1 times a polynomial x to the 0. So in general, the formula for the nth coefficient is going to be equal to the nth derivative of f at a over n factorial. So this is pretty huge. It tells us that if we want to create a series, if we want to create an approximating polynomial for any given function that has derivatives up to all orders, then the coefficients of the polynomial are related to the function by the function's derivatives divided by the n factorial, where n is the number of derivatives. So this is the big result about Taylor series. And I told you these factorials are going to be important. And so this is why. We will see a lot of factorials now, primarily because they show up in this formula for Taylor series. So let's formalize that definition and then do examples. So for a given function, f that is differentiable of all orders, so infinitely differentiable at x equals a, the Taylor series of f centered at a is given by give me 1 second. Let me see if the book, sometimes books use slightly different notation. I just want to make sure. Sometimes we use like T of X or T of F of X in some books. I don't know if we're going to worry too much about that here. Nope. Yeah, they just declare F of X equal to this. So it's going to look like Fn of A over n factorial. These are our coefficients times x minus a to the n. And starts at 0 to infinity. So the Maclaurin series for F is just the Taylor series centered at 0. So Maclaurin series, Taylor series, essentially the same thing. It's just that if we say the word Maclaurin series, it automatically means it's centered at 0. These might be good formulas to memorize. Though as a math instructor, I'm against memorization or against memorizing too many things. I think it is important to understand where they came from, understand the intuition behind them. So hopefully the build up to these, hopefully the process was fairly clear. Of course, when you solve problems, you don't necessarily want to rederive the formulas and then go through solving the problems. You kind of just want to understand how the process goes. So let's see some examples. And actually, I think this would be a good point to take a break. So maybe we'll take a 5-minute break, come back at 10:30, and then let's try to get through some more of these examples. We want to see e to the x, sine and cosine, and then maybe we can take a look at some of the more exotic functions, maybe arc sine, and then maybe these hyperbolic functions as well. And I think that would give us like a very complete list of all of the Taylor series and power series we have. All right, so we are back from break. Yeah, sucks that we have a test right after this. It's how it goes, man. I would tell everyone, every student I ever see, I tell them not to take summer math courses, like unless you're like ready to commit real hard. Because over the semester, like spreading this out over 16 weeks rather than 8, like it's literally twice as long. You have a lot more time to go over it. Summer courses are intensive. Sometimes, and I've said this a lot, that you need to just let your brain digest. Your brain learns when you sleep. I don't know if you guys notice this. If you've ever like tried to play a musical instrument or learn a skill, like a skill-based skill where it's like technical, very, you got to use your hands a lot or something like that. Like you'll notice that if you practice all day, like eventually you'll get burned out and can't do anything. And then if you go to sleep and then get up the next day and try again, it just feels more natural, like whether you're throwing a baseball, throwing a frisbee in a certain way, playing a musical instrument, it just feels more natural the next day. Same thing with math. It becomes more intuitive, and unfortunately, we just have less days. There are less number of days your brain can sleep on it and let those neurons fire and reconnect to learn stuff. So it's hard to learn math over the summer. And too bad I don't sleep. Yeah, all of us. Sleep is a big issue nowadays. I think we really need to allow our population more time for rest and exercise. Everybody's getting burned out with everything going on. So it goes. Okay, so let's do some examples, and let's start off with e to the x. This is a very e to the x is another very basic. It's a very core building block function. So kind of like the one we really had going was this exponential or this geometric series 1 over 1 minus x, very fundamental in how we derived the other ones from it. E to the x is going to be very similar. And let's just call it f of x. So the nice thing about e to the x is that e to the x is the eigenfunction of the derivative operator. So if you get to differential equations and or linear algebra, maybe you'll learn a little bit better what that means. But in Calc 1 terms, that essentially means that, of course, we know that the derivative of e to the x is just e to the x. So this is kind of an easy function to start with, and why we often start with it with Taylor series. So what was our process for Taylor series? We need to compute derivatives of n orders and then evaluate them at the base point. So we should specify the base point. Let's say at x equals 0. Again, x equals 0 going to be very common for the base point, which is why we give it a definition for Maclaurin series. So first step is to find a sequence for fn of a. It's going to be the main step. It's pretty much the only step for Taylor series. So we build up all this languages of sequences and series, and hopefully these skills behind manipulating sequences and series. And so this is why we want to practice finding closed form expressions. What do we have to do? We are computing a sequence of coefficients, and we want a nice closed form expression that we can just stick in to this formula. How do we do that? We can only do that by evaluating. So we know that f of 0 is e to the 0 is just 1. F prime of 0 is the derivative evaluated at 0, and that's just 1. If we keep doing this, we'll see, hopefully do an example of a little bit more intricate cases. We typically want to take a derivative of the previous derivative. So of course the previous derivative was still e to the x. And then we evaluate it at the base point. So we are going to get 1 again. And if we were to keep going, this is an easy sequence to generalize. What is our sequence so far? It's 1, 1, 1. What's the third derivative evaluated at 0 going to be? It'll be 1. And then no matter how many derivatives we take, we are going to get 1, since the nth derivative is going to be e to the x. And then when I evaluate it at 0, we're going to get 1. So the formula for the coefficients, or excuse me, the formula for the derivative, I should specify, the sequence of derivatives is just all ones. So that's easy enough. And then our step 2 is to plug it into the formula. So now we have that f of x is e to the x fn, the nth derivative evaluated at 0 is always 1 divided by n factorial x to the n. Most common way to write that. We pulled out the coefficients there, but sometimes you just see it as x to the n over n factorial. Either way is fine. Exercise. I'll leave the radius of convergence as an exercise. Maybe we'll get to it at the end. I want to get through more examples of this. And then if we have time at the end of class today, we can fill in any of the gaps if you guys want to see it, or we can do those in office hours. So one of the things to note is that I'm using an equal sign. It's kind of a callous use of an equal sign because we don't know if e to the x, is it actually equal to this? And if it is actually equal to this series, it's only going to be equal within whatever radius of convergence. So usually we would want to specify a specific domain to actually say that these two things are equal. For now, we'll leave it as it is. Let's move on to sine. And again, problem statement, find the Taylor series. Or let's just go ahead and say find the Maclaurin series. So centered at 0. And then, of course, and the radius of convergence. So we go through our list. F of 0. Sometimes you can do this in steps. So for example, f of x is sine of x, or like in a table is what I meant. And so now we've got f of 0. What's sine of 0? 0. Got to remember all your trigs. And then, of course, f prime of x is cosine of x. And then f prime of 0, cosine of 0 is 1. F double prime of x minus sine of x. So sometimes it helps to organize this way because we do want to compute derivatives. And then, of course, we want to evaluate the derivatives. But if we just evaluate the derivatives, we don't want to take a derivative of our evaluation. That would just be 0. So sometimes it's helpful to find a sequence of just the general derivatives of the function and then use that to determine the sequence of evaluations.
If we're not told what it's centered at, should we just assume it's centered at 0? Like if we're asked that on the homework.
Yeah, that's a pretty safe assumption. Like if it just says find a series, or if it says find a power series for the function, usually you can assume it's centered at 0, though not necessarily. If it says find a power series for the function, like in the examples we've previously done, sometimes you're doing manipulations on a previous power series and you can kind of change the center. So we saw an example of that yesterday when we were looking at 5a from the homework. But if it's a function that we have to like derive a Taylor series for, so if it says find the Maclaurin series, or it says just find a Taylor series and it doesn't specify the point, generally you assume it's 0. Yeah. Okay, so of course, if we take one more derivative from here, as soon as we take 4 derivatives, we are back to sine. And so this is a hard sequence. We haven't talked about this in lecture. You've seen some instances of even odd terms appearing appearing. We saw like arctangent had odd terms, and we haven't quite specified how to really come up with a sequence of even and odd terms. So let's work this out here. So what is our sequence? We know that fn of x, fn of 0, can write it as like a piecewise function or a piecewise sequence to try to get an idea to come up with a closed form. It's going to be 0 if n is even. So our even derivatives we see, it just vanishes. And then what's happening on the odd derivatives? Well, we know it alternates on the odd. And so how do we code that within our sequence notation? This gets into a little bit of modular arithmetic, which is related to our linear sequences. So the idea is that it's periodic with a period of 4, right? And so if we sort of divide the period by 4, well, any number divided by 4 is going to have either a remainder of 0, meaning that any integer divided by 4 is going to be a multiple of 4, or the remainder, if I divide by 4, is either going to be 1, 2, or 3. So if n is, we can write it as 4k plus 1 if n is 4k plus 3. This is going to be a little more complicated than we need, but I do just want you guys to try to make sense a little bit of this, right? If k is an integer, so think of it as a sequence or a subsequence. So if k is any integer, well, whenever I plug in a value for k, 4 times k is going to be an even number, plus 1 is going to give me an odd number. Likewise, 4k, an even number, plus 3 is going to give me an odd number. And so try to make sense of why this is all of the odd terms. And more specifically, some of the odd terms are going to have a 1. Other odd terms are going to have a minus 1. And so let's formalize this a little bit more. Our sine of x well, if we only consider our, let's write it out, our odd terms, we're going to have x minus 0. And what's our coefficient going to be? It's going to be 1. Then the next term, x squared, is going to be 0. So we can skip that one. We're going to skip all the zeros and then move on, right on to the next term. Our x cubed, the derivative was minus 1, and then we have to divide by 3 factorial. So this is, I'm essentially working through our formula just one term at a time. So this is another way you can go about doing this if you're having trouble coming up with the sequence. Write out the first however many non-zero terms. So this will help with these even and odd, weird periodicity type functions. So we are at n equals 3 divided by 3 factorial. I know the third derivative will give us a minus 1. And then it's going to alternate every on. So the fourth derivative is 0. The fifth derivative will give us a positive 1 over 5 factorial, x to the fifth. The seventh derivative will give us a negative 1 over 7 factorial. And then it's going to keep alternating like that. So how do we come up with a sequence? We keep our sum, and kind of like how arctangent was written, we're simply going to have x to the odd integers. So if our n, typically in our series, goes from 0 up to infinity and hits all integers, if the only powers of x we want to see are odd, we describe odd numbers as a sequence of 2n plus 1. And then the coefficients are going to alternate from -1 to 1 with the factorial in the denominator. So take a look at that. There are other ways we could arrive at this from our previous sort of modular step. I think it's a little more technical though. So for those of you guys who want to take a look at some of the technicalities of the sequence, happy to explain that and work through that in office hours, or take a look at that on your own if you would like to work that out. Again, all these sequences, these like 2n plus 1 and how that describes odd numbers, 4n plus 1 and how that describes all numbers with a remainder of 1 that's divisible by 4. A lot of you guys in computer science, you'll get into that, especially if you have to take a number theory course. So we've got our sign. Let's go ahead and fill that in on our sheet. Let's fill all of these in. So we have our e to the x is the sum of n equals 1 to infinity minus 1 to the n plus 1. Oh, sorry, I'm just copying the one above. My eyes are wandering. Sorry about that. Just x to the n over n factorial. Radius of convergence, you got to figure out. And n equals 0 for that. Sorry. Sine was minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. I'll give you a hint. Radius of convergence for these guys going to be infinite. So check that out on your own. You guys do have the tools now to check the radius of convergence of any of these series. Cosine, so we don't have time to go through. I'll just write it out and maybe build a little intuition for it. So we saw the derivatives of sine. How is cosine going to work out? Well, all of the derivatives of cosine are exactly the same. They're just going to be shifted. So we would start here. This would be f of 0. So 0th derivative would be cosine. This would be the first derivative, the second derivative, the third derivative, starting at cosine. Which means for cosine, the even derivatives are going to give you 1 and -1. So our 0th derivative of cosine would give us 1. Our second derivative of cosine gives us -1. So some important mathematical facts and things you should notice about this. Notice sine has all odd powers of x. And if you remember from pre-calc, sine is an odd function. This is where the terminology comes from. What is an odd function? It means it is flipped about the origin, or symmetric about the origin. So you can expect that cosine, which is an even function, has only even powers of x. In other words, cosine of minus x, cosine is symmetric about the y-axis. So you can prove these properties of even and odd now in terms of power series. If a function is even, it has to have only odd. If a function is even, it has to have only even terms in its power series or in its Taylor series. If a function is odd, it has to have only odd functions, odd powers of x in its Taylor series. And specifically with those properties, it will give us the corresponding symmetry properties that we know from pre-calc. So follow through this process. Take a look at cosine on your own. Cosine might also be in the book. So take a look at that. We can try maybe one more. We only have about 7 minutes. I don't know if we'll be able to get through. Will we get a common Maclaurin series formula sheet on the exam? Good question. Let's take a look. So the general rule is whatever formula sheet that has been given on previous exams will be given on this exam as well. So let's go to the archive real quick. And see what type of formula sheet is given for exam 3. Calc 2, exam 1, exam 2, exam 3. So from spring of 2021. Looks like they do give you a few. So from 2021, they give us the geometric series, the natural log, arctangent, e to the x sine of x. Here's the cosine one. So they write that out for you. We can add that one to our sheet. Again, look, we only have even powers of x, very similar to sine, except with the even powers. And then if you want to add any more to the sheet, you're going to want to make sure that you do it on your own. So other base functions you may want to look at. Here, let's see, where is our sheet? Here's our function sheet. Our cosine, as we just saw on the formula sheet, we should get x to the 2n over 2n plus 1 factorial. Oh, 2n factorial. My eyes keep wandering above, and then my brain wants to write. These are our base building blocks. Now what we want to do is to use both these building blocks and the formal technique of finding these Taylor series to find more Taylor series, essentially, right? We used this function to come up with arctan and natural log. If you take complex analysis, you'll actually see why e to the x sine and cosine are related. If you look at these series, they're all very similar. This is x to the n over n factorial, so it has everything, all powers of x, and then all the denominators are just n factorial. This sine and cosine has, well, this is all the even ones, even factorials. Excuse me, odd ones, odd factorials, even terms, even factorials, and then sine and cosine just have this alternating notion. So they're very similar, just with the alternating. Other ones you might want to try to take a stab at, arcsine. Arcsine just starts to get hairy because the derivatives start to involve chain rules. So this is why the techniques we were looking at previously, using these algebraic techniques and using the integral techniques to arrive at new series and new functions, are pretty useful because they can save you some time from having to go through that full Taylor series process. Because if you go through that full Taylor series process, sometimes as soon as you start computing derivatives, well, then you get a product rule. And as soon as you have one product rule for, say, the first derivative, to get the second derivative, well, then you're going to have another product rule to find the third derivative, another product rule for the fourth derivative, and it can get very hairy. So arcsine is fairly difficult to come up with. And then the other ones that we mentioned were the hyperbolic functions. Hyperbolic sine, hyperbolic cosine. Those ones may not be too bad. Right, arcsine, let's kind of take a stab at some of these and at least talk about them. We've only got a couple minutes left, so we won't be able to work some of these out. Again, if people want to stick around, maybe we can talk a little bit more about them, or we can talk more about them again in office hours. Someone says they're confused about Taylor and Maclaurin series. I don't know. I mean, so here's my desktop. I mean, this is exam 3 from APPM spring 2021. So there's series. That's a power series function with some other series, Maclaurin series. So seems like Maclaurin series, Taylor series are fair game, pretty typical on exam 3. And of course, there's the formula sheet. So just to, real quick, last minute or so, take a look at some of these other functions. When we try to work with arcsine, let's see what's going to happen if we try to come up with a Taylor series for it. Well, the first derivative we know. And so first derivative at 0 is going to give us 1 over 1. Will just give us 1. Hopefully everyone understands that f of 0 is still 0. What's going to happen? So let's rewrite this first derivative. It's 1 minus x squared to the minus 1/2. And so our second derivative is going to be minus 1/2, 1 minus x squared to the minus 3/2. But now we've got a product, so times 2x times a negative 2x. So that'll give us x times 1 minus x squared to the minus 3/2. Nicely enough, when we plug in 0, f double prime of 0, we're just going to get 0. But now we've got a little bit of an issue. What's going to happen when we take 3 derivatives? It starts to get complicated because we have this product. So now we've got a product rule. So first term times the derivative of the second is going to give us a 1 minus x squared to the minus 5/2. And we'll have a minus 3/2 times a minus 2x plus derivative of the first term times the second. So 1 minus x squared to the minus 3/2. And so f triple prime of 0 is going to give us 1. So at this level, it's going to get really technical because when we take a fourth derivative now, some of it's going to repeat. The nice thing with the product rule is now we have this term appearing again, and we have computed the derivative of this term. But now we have the derivative of this product. So we would, of course, want to combine our x's. So this will be a minus 3x squared times 1 minus x squared to the minus 5/2. We need to compute a derivative of that with a product rule. And then ideally what you would want to do is compute out a few of them. So the fourth evaluated at 0, should probably expect it's going to be 0. Again, this is actually using the even and odd properties of sine. Arcsine is still an odd function. So you have to compute your fourth derivative and then somehow justify why we see the sequence of derivatives that we see. The hyperbolic functions let's do hyperbolic sine, I guess. Those ones may not be too bad if you just remember that hyperbolic sine is e to the x minus e to the x, e to the minus x, all over 2. Hyperbolic cosine is e to the x plus e to the minus x over 2. So taking derivatives of this isn't too bad. And if they taught you in Calc 1, if they taught you this in Calc 1, you should know that g prime of x is hyperbolic cosine, g double prime, hyperbolic sine. That the derivatives, the nice thing about the hyperbolic functions, hyperbolic trig, sine and cosine just alternate. There's no negatives that appear. So those derivatives are fairly easy. And then evaluating them is fairly easy. Let's see. Any other ones we might want to look at? Tangent is kind of hard. Again, because what's going to happen, the derivative of tangent goes to secant squared of x. And then the derivative of secant squared is 2 secant of x times secant tangent. And now you have a product. So as soon as you start with one product rule after you take however many derivatives, you're going to just have product rules every consecutive derivatives. So those ones can be a little tricky. The other way to do tangent is to use division. But then you have to do long division of power series. And that is going to be very technical. So we won't give you something like that on the test. We are kind of going to be checking on the test. Do you know the process of finding the basic process of finding a Taylor series? But again, we will continue Taylor series on Tuesday. So maybe we'll take a better look at some of these complicated ones and how we can do now division and some of these other algebraic and differential tricks to come up with new Taylor series. As we mentioned before, coming up with products of power series, not easy to do. Coming up with division of power series or Taylor series, not easy to do. So maybe we'll touch base on that. And actually, we can derive it. The geometric series is a good one to start with in regards to that. But otherwise, I think that's about it for the basics of Taylor series, all the power series, anything that could be covered on the midterm. Any questions?